Hi everyone. I'm Rob Schubert. I want to thank Fred for providing this platform for my presentation. This is overview of reliability functions for life testing in Minitab. I'm going to just switch my camera off and we'll just go into this. So our agenda is an intro into reliability. We are going to discuss selecting a distribution, testing to failure, right censoring, and testing to failure, arbitrary censoring. I'll go into both of those and what they are. Accelerated testing with single factor change and accelerated testing with multiple factors. And I'll try to give you a little summary of what we covered, and we'll have some time for questions, hopefully. So as a quick intro to reliability, reliability is, a lot of people like to describe it as quality over time. Things out of the box would be quality. Things that happen over time, a failure that happens, several hours into use would be considered reliability. A lot of people discuss the bathtub curve where they have early infant mortality failures, and then there's a constant / random failure, and then what would be considered wear out failures are the last. And if you add them all together, you get the observed failure rate that looks like a bathtub curve. Now, a lot of people can tell you that that's not a real common thing necessarily, but if you can break it out into those things, sometimes you can find these different failure modes. So we talk about field failures, and what those field failures we discuss are failure modes. From those field failures, we try to decide or replicate those failure modes with testing. So in the case, we'll show some examples. In case of what we want to do is so we can determine if there's any kind of improvement, if we make changes, things like that, and replicate that through testing. And then you measure time to failure, and then you can attempt to predict a new failure rate from, say, new data. Probability distribution function is a function that describes the relative likelihood for this random variable to take on a given value. So you commonly see something like this, which is a normal distribution. And then there are different values of sigma, which is the spread of the distribution that will cover a specific percentage range. So if you integrate, say, from -1 sigma to 1 sigma, you will get a 68.26% probability that will be in that range. So in reliability, we don't generally focus on the normal distribution. There are many different distributions that have been developed over the years through statisticians, logistic, log logistic, Weibull, gamma, log normal. Very commonly, you'll see Weibull in reliability or log normal. There's different ways that you might visualize the data. So what I showed before on the normal distribution is the instantaneous probability. So each point would have a specific percentage for that particular failure rate. Let's say something that would be a beta of 0.05, this is a Weibull distribution, has what looks a lot like a infant life mortality. And then when you get on to a beta of 3, you're looking more similar to what might be a wear out failure. And if we look at different ones, the cumulative probability is something that you might make more sense to you, something that is wear out, as you can see, has a long period of no failures, and then it ramps up to something that would be all failures. And then a lot of people like to use the straight line cumulative probability. Now, that's my term, but it takes that line and makes it a big straight line. So these are all the exact same probability distribution functions shown in different ways. You kind of just stretch a line and it pulls the probability into a straight line. Now that's because the X scale is specific to a Weibull distribution so that it comes out as a straight line. So the shape is also known as the slope, and the slope is when you take this straight line cumulative probability and you can see that the three different beta values give you different slopes, like a mx plus b kind of slope. Oops, sorry. And then a hazard plot is something that is really similar to what you would see for, it's a cumulative plot where you have the infant life and the wear out failures and the random failures and different betas, as you can see there. A scale, now the scale shifts the plot out or to the left or to the right. This kind of tells you more about how a specific, oops, I'm sorry. This tells you how that the data is lasting longer or such that you would have the same beta slope, but you could say that it would shift out. And so sometimes if you do a corrective action, you may see your scale shift out, and that would say that yes, you've increased your reliability. Threshold is the third parameter that we don't usually use. It's sometimes very helpful. You can see there that the eta is shifting the 0 point basically. So that let's say you have a Weibull distribution like this, you would might say that if we did a bunch of data testing and we find that we can fit, and we're talking like maybe 100 data points, that you could fit a distribution where you have a eta, you may be able to say, okay, for future testing, let's say your supplier, you might say, I don't want anything less than 5 because that would show that my reliability would be lower. It's forced 0, so when you say a 2-parameter log normal, it's just called log normal. Exponential, Weibull, gamma, and log logistic all have what is called a third parameter. Of course, exponential is actually a second parameter. It's not represented on the straight line cumulative plots, so you will notice that if you plot this in Minitab, it will say the scale minus the threshold on all your plots. So testing to failure, what is censoring? So what in reliability we call censoring, where we don't end the test at a failure. Let's say you run 100 samples and only 50 of them fail, you don't have to throw out those other 50 data points, you call them censored. Some tests cannot be continuously monitored. So let's say you want to test something, but check it every 50 hours to see if that thing has failed, you would use arbitrary censoring. Distribution identification. So there are many distributions and more. So which one would you use? So Minitab, which is mostly what we're talking about here, and I should mention that a lot of companies use Minitab for quality purposes. So even if you, let's say you're the sole reliability engineer, but there may be several quality engineers, it may be already software that your company has. It's a lot cheaper than some of the specific reliability ones. I say it's probably 1/10 of the cost of Reliasoft. So it's common software for companies to purchase. So there's many distributions. Which one would you use? There is a function in Minitab that will help you with this. So what do you know about your data? Reliability data starts at time equals 0. Is it bound? It's bound by 0, of course. There could be something greater. Any historical references. So a lot of times it's important to look at the historical references that you have. I'll talk about that a little more later. Does it fit is one of the questions that we have. cost of Minitab. The cost of Minitab, I just looked up, is around 1,200 a seat. 1,200, yeah. So, but that, talk to Minitab. I'm not a representative of Minitab. I just use Minitab. I find it very useful. Statistics to look at. So the Anderson-Darling test is how well your data fits the PDF. Smaller numbers means that it fits better. So if you find your Anderson-Darling test has a 1 for or 100 for exponential, that usually means it doesn't fit, but they're comparative results, so your doesn't necessarily mean that one is good. It's just comparative to the next, to the other distributions. The p-value is the student's t-test. Does your data fit the PDF? So in one of the distribution identification plots, it will show you the p-value, and the H0, the null hypothesis is that the data fits the distribution. P is low, the null must go. If P is less than 0.05, it doesn't fit the distribution. So pay attention to the p-value. And then the likelihood ratio test is a p-value also. It's the question, does the 3 parameter fit better than the 2 parameter? The null hypothesis is the 2 parameter fits better. If it's less than 0.05, the 3 parameter fits better. Here's an example of what is called a wire scrape test. This is ISO 6722. You may have a cable and it may get frayed in the field, and in this case we wanted to replicate that failure. We found this linear Tabor abrasor. It measures cycles until breakthrough. It measures continuity between the scrape head and the wire. It's specific for shielded cables. You can do it visual inspection if you feel like it, and that would obviously become arbitrary censoring. In this case, we did to scraped through to the shield, so we would know exactly when it failed. You can look at ISO 6722 if you are interested in this test. So we wanted to identify the distribution. It was a new test to this particular company. So we took several data points. We wanted to identify the distribution. We looked at the graphs. These are the 3 steps to identify the distribution: to look at the graphs, look at the warnings, and look at the Anderson-Darling numbers. This is done through stat, quality tools, individual distribution identification. On the left of this screen, I have given you the data, this data that we're looking at today. So if you want to look at that from the plot or from this presentation, you can look at this data and see if you can do it. I'm gonna look at the questions quick. Yes, it's true. This is mobile phones can use this if they're interested in their qualities for their specific cables. And then so once you get into individual distribution identification, you have to choose the column and the subgroup size. In this case, subgroup size, I chose 1. That means all the data is in one subgroup. That's more of a productions kind of thing. So I usually use subgroup size of 1. And then you can say use all distributions and transformations. There's some that I don't look at all. I'll tell you which ones those are. And then there's some that you might be more specific to this particular problem. So this is what it pops up. It pops up all these graphs. I also want to mention that all this presentation has been done, I believe, in Minitab 16. There was a question on what version. There's Minitab 19 out. It has a lot more features, but I did pass this by Minitab themselves and said, is any of these specific functions changed? And they said no. There might be formatting changes, but there's not anything that would be different than what I'm presenting today. So if we look at these, we can actually tell that some of these, such as the exponential, doesn't fit this data at all. So we can X out a bunch of these that kind of show either a curve or the line doesn't go through it at all. So we can just skip these distributions. There are some warnings. So in the session window, warnings pop up. And these warnings, I used to ignore them, but later I found out that specifically these warnings are telling you that this is not converging, so we've just given you kind of a garbage data. So I wouldn't use these distributions. So then at that point, we can X out these because of the warnings, which leaves us a good handful of distributions. So I will go on to what the Anderson-Darling test shows you. This is the Anderson-Darling results. Like I say, Minitab 19 might be prettier looking. This was the results from Minitab 16. You can see that there are several distributions that we didn't X out, and I drew the lines myself through these. But there are several that show different Anderson-Darling results. The lowest being that the Weibull and the 3-parameter Weibull look pretty good. Likelihood ratio test says that if it's less than 0.05, the 3rd parameter fits better. In this case, we can see that it's not different. So we're going to use the Weibull distribution, which is the most common distribution that reliability engineers use. It's good to stay with the common ones. It gives you less talks about why you chose your distribution if you use the most common one. So this is good that we found that this one fits the Weibull distribution. Now, alternatively, we can use what is a distribution identification in Minitab that's a reliability survival. Now, this is different in different ways, but I'll show you that in this case, it ended up with the same answer, which I believe in most cases, it'll end up with the same answer. Why, and I'll tell you why you might want to use this instead of the other distribution identification. So in this case, we'll put in the variable wire scrape. We are going to go into the options. So the options plots will show you that you can choose an estimation method of least squares or maximum likelihood. And that's what we'll look at first. I chose maximum likelihood in this case because of the in this case, I have a lot of data. So the small samples without censoring, at least squares, might be a good choice. It's got a better graphical display. The maximum likelihood has more precise than least squares, and is better for heavy censoring. And the MLE allows you to perform an analysis when there are no failures. So you can actually get results that you have no failures in. This is the plots once again. You can see that in several cases like exponential and whatnot, they have the same kind of non-conformance to the line that we were looking at. We can X those out immediately. And then we can look at those warnings again and see that these have several of them have errors that we would decide that those aren't acceptable. So those are the errors. So we have 5 distributions still available for us to look at. I'm sorry, I'm going to scroll through the questions. All right, I'm not covering ROI in this presentation. I will say that would be a different presentation. And Minitab in South Africa. As I say, I'm not a representative to Minitab, so please direct those to Minitab themselves, which I have discussed with them, and they're pretty nice people. This is the result of the Anderson-Darling test. Weibull again shows, and the Anderson-Darling is the highest. We also see that 3-parameter Weibull is high, which is what the results we got on the last one. A 3-parameter log normal and a normal distribution all have the same Anderson-Darling results. Now this is using an adjusted Anderson-Darling statistic. They're different because there's a different algorithm because of censoring that it uses here. There's no p-value, there's no likelihood ratio test in this case. If I were to go ahead with this, I would say, again, Weibull distribution, but more likely to use the quality version of the distribution identification to choose this distribution because of the p-value and the likelihood ratio test exist in that analysis. So here's some other output, and I just want to cover this, that it will give you percentiles. You can add in specific percentiles that you want to look at. You can look at the MTTF, not necessarily something I would say is useful other than you want to compare what your results are with these outputs, that you can see that we're talking like a maximum of 2 change in the mean from different distributions. So, and then at the first percentile, let's say you have a failure rate target of 1% failure rate target, you might want to look at the L1. In this case, we're not seeing a huge difference, we're seeing 20, in the range of 20 difference between these. Now, when you get below 1%, you're talking about things that are getting more difference over the distance from the center point. Your confidence intervals get larger as well. So that's why you might see more of a difference as well. Now, so I also want to mention that the third parameter threshold is not commonly accurate for sample sizes below 10. I've done a different study to look at that. We want to use samples of 20, greater than 20, maybe to get a 3-parameter Weibull to fit well. So many of the distributions are very similar. I just want to point out that, you know, a Weibull distribution and a log normal distribution almost look the same in some cases where your parameters would meet. Their similarity is really similar. Just so that I want to also point out that the distribution identification isn't going to be a huge make or break you in analysis. So it might be good just to go with the Weibull distribution because of the consistency with reliability functions. The log normal is good for things that are flex, like bend. That's commonly found in literature. So a lot of engineers, reliability engineers, use Weibull, and then I would recommend log normal for some of these flex life kind of things. Again, I recommend using the stat quality tools individual distribution identification since it has the p-values and the maximum likelihood. But if you have censored data, you'll have to use the other one. Testing to failure of right censoring. So as we discussed this earlier, some of the tests cannot be run to the end due to constraints. Some things just never fail, which is good for you. Some tests cannot be continuously monitored, arbitrary censoring. So we're going to focus on right censoring right now. This particular data set I'm looking at is the cable flex test. So it's a mil standard 915. This particular test, you check for continuity continuously. The failure mode on this particular test machine I had was an open on the conductor. There's also the short condition, which was a lot more uncommon for this particular cable. Of course, yes, that would be an idea to check that as well. Each independent Each unit was independently checked every millisecond in this particular test machine. I had a limited number of samples. I think it's 10. I did a distribution analysis, parametric distribution. So we're going to look at right censoring on this, which you enter in the cycles, and then you enter in the quantity. So in this case, I stopped the test at 281,000 cycles. So those three cycles were units were suspended, and then I had a quantity of 3 in that case. You could write all these with a single value. So you could have 3, 2, 8, 1, 4, 5, 7 entries, and then not use the quantity feature in this particular program. I assumed the distribution was Weibull. This was based on some historical data and doing some analysis on historical data. I also want to mention that I like to use the same distribution for a specific test. If we use the specific test over and over again, I would recommend using the exact same distribution every time and not necessarily doing the distribution identification every time and changing it. I would say use the same distribution for all tests. It might be good to use several tests to identify what distribution you want to use for that specific test. In this case, you go to the sensor button, click the sensor button, you have to enter SUSP, that's the column header, and then the quote S unquote. And that's kind of irritating that you have to put the quotes around it, but if you don't, it won't recognize it. In this case, I used maximum likelihood. Again, I had a decent amount of data and I had a limited number of sensors. Oops, okay. Better graphical display for these squares, better for small sample size without censoring. So I have censoring, so that's why I chose maximum likelihood. And this is the results, and you can see that it fits the line fairly decently. This is also the cumulative failure results that you'd see on the right there. These are the results of the session window. It shows your shape and your scale. Your mean and your medians are just something you might be interested in. If we're doing comparisons, it's maybe a useful characteristic to compare things, means and medians. You may pick a different L10, L1, different places that you might want to choose for comparison, depending on your needs for your company. And here's the table of percentiles. Again, you can look at the 1% and all the way up to the 99%. And the 50% should match your mean, or your median. Testing to failure. So this is arbitrary censoring. In this case, I had a step drop test in a particular unit, not exactly pictured here, but I wanted to show you something that would be what you might be testing. Drop on the connector, we did 10 drops at 40 inches, then we did 10 drops at 50 inches, 10 drops at 60 inches, etc., until failure. I tabulated this data, so I had unit number 1 drop 10 times at 40 inches, 10 times at 50 inches, 10 times at 60 inches until it failed. Everything that we had failed before full set of 10 at 60 inches. So I made an arbitrary censoring where I had total inches passed and total inches failed at. So now I have a range of 12, say for the first one, 1260 is the lower end, and the upper end was, sorry, let me go back to this. 1260 to 1320. And then using the minor rule and cumulative energy, we added up all those values. 1260 being 40 times 10, 10 times 50 plus 60 times 6 is 1320 actually. And then 60 times 5 would be 1260. I took that data, we used it for arbitrary censoring and parametric distribution analysis. At this time, it didn't have a good set of data that I wanted to use the distribution identification on. So I used the standard Weibull distribution on this one. So the total inches passed is the start variable and the total inches failed is the end variable. Frequency column is blank because I didn't have any repeats and I didn't need to put a number in there. I didn't have any suspensions, so I didn't need to go into that. This was the results of those particular drop tests. And then we can see that it has a shape and a scale, cumulative failure by total inches passed. I also wanted to mention that arbitrary censoring versus right censoring, how is it different? You can see that if I just run the right censoring on total inches passed and total inches failed and the average between the two, they're all very similar results in this case. There's a little shift right or left depending on which one you're looking at. So there's not a big difference. There's a wider intervals if the range gets bigger. Do a quick stop. Did I see a hand raised? Oh, here we go. Sorry, it's my first time running this webinar. All right, I was audio and everything looking fine. I'm sorry, I just seeing a lot of comments that way. Okay, I'm gonna move on. Acceleration factors. So Minitab has some accelerated test functions in there. Reliability engineers attempt to speed up testing by accelerating the test. It might be environmental with increased temperatures beyond, say, what your customer might use. You can use increased temperature with the Arrhenius function. A temperature swing might be used for the Coffin-Mason function. You can add environmental factors together and some sequential testing using Miner's rule. And sequential testing. Mechanical, you can use increased speed or increased rate or maybe others. And sometimes you might use multiple factors at the same time. This is back to the wire scrape test that we talked about before. There is a specific weight that goes on top of this. So you can use different weights and see what the acceleration factor of that is. This is done experimentally.
Hey, Rob.
Yes.
Looks like you're out of presentation mode and your slides aren't advancing.
Oh, okay. Thank you.
Yeah.
Should I go back at all? How far did I go back?
Well, start with your acceleration factors. That'll work.
Okay. I'm sorry. Reliability engineers attempt to speed up testing. Is it looking good now?
Yes, you're good.
Okay, thank you. Reliability engineers attempt to speed up testing by accelerating the test. Environmental may be used, like the increased temperature of the Arrhenius function may be used beyond what your customers might be using. Increased temperature swings beyond what your customers might have. You can add these environmental factors together. Sequential testing also can be used to accelerate reliability testing. Mechanical, you can increase speed such that, let's say we go back to a wire scrape or the flex test, and nobody is flexing every 40 times a minute for a flex test. So that would be an accelerated. How that relates to the field is another question. I'm not covering that right now. That I have a different discussion about. You might have increased weight and others. There might be multiple factors you want to look at the same time, and I'll cover that. The wire scrape test is a test that uses different weights, and what effect does that have? So in this case, we wanted to decide what the effect of the weight was. So you could say, let's say you have a test that runs, it takes a day to finish. And in this case, let's say, oh, there's some really bad wires you're looking at and some really good wires you're looking at. So the bad wire, let's say you use a really lightweight, the 0.85 kilograms, it scrapes through in 10 cycles. And then you have a really good wire and the 0.85 could take, let's say, 100,000 cycles. And you don't want to wait for that to finish your 10 samples or your 20 samples or your 50 samples. So you can use an acceleration factor so that you can have more gradients into your testing so that, let's say we use the 1.25 on this other cable and it breaks through in 100 cycles, that might be something that might be useful to speed up your testing, but you might want to compare that to that first sample and say how much better it is. So using acceleration factors can do that. This is some particular data that I have on the right. There's cycles, there's weight. Now the weight is, I'm sorry, it's an eye chart, but there's 4 different weights there. So we're going to use the accelerated life testing function in Minitab to identify what the factor weight is having on this particular thing. So we'll look at reliability survival and I'll go into stat, reliability survival, and accelerated life testing. You get this box to pop up and then you enter the cycles as your start variable. The accelerating variable is weight. The relationship we use is linear. There's a radius in there and there's linear, and I think there are maybe 2 more that I'm not covering here, but you can take a look at those and see what kind of help they have on there, because their help is actually really well written. In this case, I use the graph where I'm just looking at the 50 percentile mark. You know, it preloads you with like 10, 50, and 90. That graph gets a little bit clouded, so I just bring it down to the 50% mark. I like to display the failure times on the plot so you can see where the actual dots are. It also can give you a probability plot at each accelerating level based on the fitted model. So let's look at that. Oh, and I assume distribution is viable. We used that before. So here's your straight line plot. In this case, you can see that the 0.85 does a lot more cycles, say, than the 1.25 cycles. And it uses a common slope. So it's calculating the slope off of all these samples based on a common slope, trying to fit to all 4 lines together. That's the right way to do it. You can see that the 1 pound one doesn't quite seem to line up exactly how that was done. Might need more investigation why that is. There's different things you can do to look at that. And then on the right side, you'll see that there's a relation plot that shows you the cycles of that 50% mark, and the weight, and the 3 lines actually are the confidence intervals around that. So you can see that that graph is shown, and we can look at what we can look at are the predictors. So we will take this little plot from the session window, the text from the session window, and we'll look at the shape, weight, and intercept, and we'll put that in a equation. So the prediction becomes exponential function of the intercept. Say, move these down here, and we'll say the intercept is 13.0887, and the weight function is providing a negative 6.03, and then there's the shape function has an error term. That is basically gives you that shape function. So when we take this equation and we put the error term, there's different error terms for 50% mark, the 90%, 10%, all the different marks. Put the 50 percentile mark of negative 0.3665 in the error term, and we can actually calculate the predicted cycles at each weight and even weights that we didn't test. So we'll take that and we can go back to what most commonly used are acceleration factor that you would calculate from these predicted cycles. So I'm going to say the acceleration factor for 1/4 kilogram can be calculated by taking the difference between these 1/4 kilograms and dividing them. So 2504 divided by 45,332 gives you 4.52. So we take that and we can do that calculation, and that basically happens all the way down the same. If you calculate those, it'll give you that acceleration factor. So the generic acceleration factor in a traditional sense would be 4.52 from this data. You can also do the acceleration factor per kilogram, and that's 418. All right, just a quick. All right, I'm taking a quick look at questions. The prediction for cycles at different weights is cycles when the DUT failed. Yes, so this is the 50% mark. So 50% of them would fail at these particular prediction cycles. So at 1 kilogram, 1,001 cycles, 50% of them should fail by that point, based on the distribution that we chose, based on the calculations. So you can also do multiple factors at the exact same time. In this case, we're going to look at these multiple factors. This time I'm going to look at the cable flex again. So we can vary the mandrel size, which is the bend radius, or we can vary the weight. So weight could change. That'll accelerate the test. The tighter mandrel size or the tighter radius accelerates the test as well. Go into stat, reliability, accelerated life testing. Data is to the right here. It is too small to read, but if you take this presentation, you may be able to copy that out and do these exact calculations. Put in the cycles, quantity for frequency, and then we're going to do a linear accelerating variable of weight and the mandrel in millimeters. Linear relationship as well. That's the second variable. We'll look at the graphs. Again, I'm going to put in a relation plot, only 50%, probability plots as well. And we look at this, and we can see that there's a couple of sets of data there. we have weights, we have mandrel size. In this case, I had two different mandrel sizes. I had 4 millimeter and 25.4 millimeter mandrel size. You can see the cycle life was significantly different due to the mandrel, of course, because there's significant difference there. And then we used 3 different weights on different mandrel sizes, so we could see that there was a relationship between mandrel size and the weights. Look at that regression table again, so we can get this prediction equation. With the exponential function, we'll take the intercept, the weight, the mandrel size, and the shape, and we're going to do the calculations so we can actually determine these acceleration factors, again, in the traditional sense. So for every half kilogram, we can do the division between the half kilogram numbers with the same mandrel size and get by 2.28. That also works with the different predictions with different mandrel sizes. As long as you keep the mandrel size constant, you'll get this acceleration factor. If you want to look at just the mandrel size, I'm doing a 5 per every 5 millimeter mandrel increase. We're looking at a 2 increase. So that gives you that traditional acceleration factor. So every time you get 5 millimeters of mandrel increase, you get double the cycle life. With the weight, every time you add 5.5 kilograms, you'll get a little over double the cycle reduction. These are point estimates I want to mention. I haven't put in the confidence intervals because it gets a little clouded after that. Take a quick break for questions. So let's talk about Arrhenius. So Arrhenius, that would have to be, you do not need necessarily field data for activation energy. You need different levels of temperature. So if you do a test and you're running it with a particular temperature and you want to calculate your activation energy, you do that with different temperatures. So it fails in X number of hours for, say, 10 units for temperature A, and temperature B, it fails in longer number of hours. Then you could calculate your activation energies. And that can be done in Minitab because there is, like I showed the linear, there is a Arrhenius equation input you can give to it. All right. So the summary, distribution selection can be assisted with statistic, but knowledge about your data is key. Like I said, commonly choose Weibull, log normal for different things that because of the history that reliability is used to those particular distributions. Right censoring is used if an exact count is available, arbitrary censoring for periodic testing. Accelerated testing can provide faster answers, and testing at different levels can assist in understanding the relationship for that acceleration. This is a little bit about me. I'm a certified reliability engineer. I worked at Ford Motor as a Six Sigma black belt. I was there for 13 years. I was at Shure for 13 years. I'm currently not at Shure. So I'm still looking for opportunities if there are any out there. I have done 3 previous presentations. This exact presentation, well, a little bit modified, was done for Minitab Insights Conference in 2016. I also did practical use of stress strength models to develop specifications. Maybe that's of interest to this crew. I may work with Ascendo Reliability to try to bring that one together too for a presentation for all of you. Any questions?
So, hey, Rob, this is Fred.
Yeah.
And I just discovered I can't send you a question on the questions tab. So I just turned on my microphone. So pardon my interruption. Um,
No problem.
I know that some software packages like R or Mathematica or those things are really powerful and can do all kinds of cool stuff, but they also have a steep learning curve. And I mean, you went through a bunch of different examples here. How long did it take you to sort these out and figure out these were the appropriate ways to fill out the data? How long did it take to learn and get up to speed with Minitab?
Um, I think it's a quick learning cycle, which is one great thing about Minitab is that you can copy and paste from Excel back and forth. And there's even a function in Minitab that I use commonly for sorting data. If you, yeah, sometimes it wants it in a certain format. This can take columns and stack them and put like, let's say you have the weights that are different weights. You can make them in different columns. This can unstack them and put them in different columns, or it can take them and stack them and say, here's four samples with this weight. Here's 4 more samples with this weight. So it stacks them and puts that subscript with them. Minitab is very specific in some of the ways it wants to see the data. It has the functions to help format it right for them. Learning these particular functions, I mean, I gave you enough information basically to use all these functions right now if you had the software. And so I think it's pretty easy software to work with. There are different, like understanding Arrhenius equation and the Duquesne model and various acceleration factors is outside of the scope of Minitab. It will let you calculate whatever you want, however you want. It won't tell you you're doing it wrong in that case. Um, there are other things that similarly it won't do, like your selection of your distribution. I told you how it was done. It doesn't select distribution for you like Reliasoft does. Reliasoft will pick a distribution for you. Now there's parameters that go into that, like they'll say weight it this much and weight it this much in Reliasoft. A lot of users, I'm a minor user, I didn't use it that much. I understood that. I used their presets because who am I to know more than them on this particular subject? Um, so there's that goes into Reliasoft that kind of is manual in this case for Minitab.
Yeah, and I mean, it's the level of sophistication of the tool, and that's
Mm-hmm.
nothing wrong with it. But I think you touched on a key point, though, and one, I would not just follow the presets in any software package without understanding it, right? I think that you were talking about that more in the selecting of the distribution. And it's
Right,
the same with Relisoft. It'll do its wizard and it'll say this one appears to be better for you. But if you've got 15 sets of data and 4 technical papers that all say it should be a 2-parameter log normal, and just because the gamma distribution fits this particular piece of data better or set of data better, doesn't really mean that it's the right distribution. It doesn't know the
right,
physics of what's going on, right? Or the
mm-hmm.
chemistry of what's going on. So
Right,
I think that needs to be stressed is that it's a tool, right? Minitab
right,
or any of these things are tools, and it comes with your engineering knowledge, not just statistics, but what's what's the failure mechanism you're dealing with,
Right.
right?
Yes, exactly. I mean, like I said, I like to pick a specific distribution for a test, um, and not vary from that based on data from another test. Like if you have a historical, we've done 10 tests and they all fit Weibull pretty good. Sometimes I would use the distribution identification across like 10 tests and say, oh, well, 8 of these say Weibull and one says something else. I'm going to use Weibull for all of them. And
Yeah.
that's, because the variability of the test can just give you, you know, information on that particular one might be not exactly what's correct.
Yeah. Now there's a caveat there, I think, is that well maybe those that one or two tests actually had some other phenomena going on, right? Is there a rationale or a reason or a physical or chemistry reason why it's different? And if it's not just different, it's just it could be just the randomness of actually doing testing and not having a lot of samples that the data doesn't quite fit like as well as it usually does. And that's plausible, yet I think it's prudent to say, could it was it a humid day, for example, when you're doing wire
Yeah,
scraping, or was it something else that is another variable that we're not accounting for? You have to
that's true.
constantly question your data and
Yep,
ask those kinds of questions.
I agree with that.
Okay, looks like Christine liked your review and agrees that it's simple to learn or easier to learn. Um, yeah, when I first started with our software, it was only in a command line language, and it was basically learning a scripting language or a programming language. It's gotten better. There's ways to improve that, but it's still a steep learning curve compared to Minitab. Now, the other piece here, Robert, is when you showed some of these screens of how you set up the data in Minitab, they had all these um, drop downs and radio buttons and options and so on. Um, I mean, you could spend days and days and days talking about all what it could do and all the different circumstances. And I know that Stephen Wax, when he did the process control class, went through in some of the options and details and nuances of all those options. You just scratched the surface of what the software can do.
Right, yeah. And, you know, um, this is, yeah, it's kind of generic. And I did gloss over some of those choices. Um, but some of them presets are fairly decent to begin with. So
Mm-hmm.
I feel like you can get going with this and not make some huge mistakes. As proved with some of the distribution identification, even if you choose the wrong distribution, you'll probably still get a very similar answer.
Yeah, that was interesting. It's uh, years and years ago, I shared a data set with a friend of mine to take a look at it, and because I had some questions about how my analysis was going, and he was using, I don't think he was using Minitab, he was using some other package than what I had, and we compared answers, and we had um, slightly different answers. I mean, here you had pretty similar answers, but it's all with the same basic underlying algorithm. It's the way they implemented the MLE so that
Hmm.
you got similar treatment across all these distributions. When you go to different packages and you did both, we were both doing Weibull analysis using the Weibull distribution, but our beta value, that slope, was like 2.1 versus 2.6. So it was
Wow.
quite a difference.
Hmm.
And we double checked. We wanted to make sure one wasn't doing rank regression and the other one was doing MLE. And we tried to do it exactly the same, but we still got differences. And that speaks to how individual software packages
Yeah.
implement these algorithms.
Yes, there is differences. There's even within Minitab, it was like, why are the two Anderson-Darling tests giving different results? And um, one's adjusted and one's not. But you could theoretically try to compare the two and say, well, what's going on there?
Yeah.
So yeah, there's different. I'm sure there's probably even different statisticians at Minitab themselves that are doing different things at different points of the software that probably should be combined. Um, yeah, so yeah, each software package has their own statisticians and they're all on the forefront of statistics, so it might be slightly different or even majorly different in certain cases.
Well, it's double check it. I always tend when I open up a new package or try a different feature in a package, is I try to find an example someplace that has been worked out. So like accelerated testing, I go to Wayne Nelson's book because he has worked out, and he did it manually, right? And he
Wow.
has worked out examples, and he uses some software on occasion. Or I go find a technical paper that shows a rigorous peer-reviewed analysis, for example, and I run that data to see how is it doing what I expect it to do, rather than just saying, oh, dump it in there, push the button, and that's the answer. I
All
tend to
right.
want to understand the algorithms. And one good thing about Minitab and Jump, it's Big Brother software, is it's pretty well documented. It goes
Yes.
into detail, way more detail than most people want to get into.
Yeah, totally. I agree with that. They have really good help files that I've pulled some of this exact stuff out of there. So just to understand, what is a MLE versus least squares is probably straight from their help file.
Yeah. 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 We sound like we're trying to sell Minitab, but we don't have an affiliation with that.
That's
Um,
correct.
Yeah, and Christine noted that she appreciates the warnings about how to use these packages and understand what they're doing is as important as just using the package. So I appreciate that. So it looks like questions are slowing down, and we're coming up on the end of the hour. So Rob, any last thoughts here before we sign off?
No, that's I think that's everything. If you want to tell Fred how interested you are in the other presentation I mentioned, which was stress strength models and target setting, let Fred know, and we'll see if we can set that up.
Yeah, no, I think it would be interesting. And I'm trying to think next week. And I do this every time, Rob, is I completely blank on what the next upcoming webinar is. If you go to accendoreliability.com and go over to webinars and upcoming live events, you'll see all of the stuff that we've got scheduled. And right now we're scheduled out into July already. So we've got more webinars coming, and we look forward to having you all join us. And so thanks so much, Rob, for putting this one together and presenting it to us. Gives us a good feel of what's going on with Minitab and doing reliability. So it's got a lot of nice features. So certainly appreciate that. And so to everybody, and you too, Rob, is enjoy the rest of your Tuesday. We'll talk to you all later.
Yep, thank you much.